We will continue our study of capacitance by looking at energy of a charged capacitor. Well, obviously, when a capacitor is charged, it contains energy. It is capable of doing work. A charged capacitor can light up a bulb, can drive a motor. Is that right? It can do many different kinds of work. It can do work because it acquires energy while being charged. So, the question we are trying to answer is, what is the energy stored in a capacitor? In order to charge a capacitor, work needs to be done. How is work done? We need to transport charges and put them on the capacitor plates, and that needs energy. So charging a capacitor, you need to spend energy. That means you store energy in the capacitor. Work done in charging a capacitor is stored in it as energy. Now, let Q be the amount of charge on the capacitor of capacitance C. So, let us say, to begin with, the capacitor plate has an amount of charge Q and its capacitance is C. Now, remember, capacitance is a constant. Now, the amount of charge Q raises the potential of this conductor. I have just taken one capacitor plate. The amount of charge Q raises the potential of the capacitor plates to V. Now, what is the definition of potential? Potential is defined in terms of work done, isn't it? Potential is joules per coulomb. How much work needs to be done to move 1 coulomb of charge? Now, if potential is V, means if you now want to move 1 coulomb of charge and put it here, you need to do V joules of work. That is the meaning. So, as the potential of the conductor increases, the work you need to bring in more charges to the capacitor also increases. So, if Q is the amount of charge on a capacitor plate of capacitance C, then the potential of the conductor will be V equal to Q over C. Now, if you want to now transfer an additional charge dQ, remember this V stands for what? Work done per unit charge. If I want to move 1 coulomb of charge now and put it on this capacitor, I need to do this many joules of work. Now, if I want to move an amount of charge dQ, the amount of work done will be then V times dQ. So, dW, the amount of work done to move a charge dQ, will be dW equal to V dQ. That means if I want to move this small amount of charge dQ, I need to do an amount of work dW equal to V dQ. That means each time I move a charge dQ, it raises the potential. That means next time I want to move another dQ, I need to do a little more work. So, as the potential of the capacitor increases, in order to bring the next batch of charge, I need to do more work. So, in order to find the total work, in order to transfer a total amount of charge Q to a capacitor, the amount of work can be obtained by integrating dW. Is that right? So, integrating dW from, say, V1 to V2, the potential increases from V1 to V2. And we can show that it is equal to 1/2 CV squared. Well, I think you need to do that. Let's see if we can do that. So, to move a small amount of charge dQ, the amount of work done is V dQ. And so, if you want to find the total work done when the amount of charge increases from an amount Q1 to an amount Q2, what all we need to do is integrate this dW from Q1 to Q2. Now let me do that on the whiteboard. Now watch these steps. The total amount of work done when the amount of charge increases from Q1 to Q2 will be integral Q1 to Q2 dW, and that will be integral Q1 to Q2 of dW is V dQ. Now, in order to work out this integral, you know that V is a variable, Q is a variable. Now you cannot have two variables when you want to integrate. So what we need to do is replace this V in terms of Q, because we are going to integrate with respect to Q. Can you give me a quantity which I can replace V by? Well, you know capacitance C equal to Q over V. Therefore, V can be written as Q over C. Is that right? Yes, let's do that. Well, you know that C equal to Q over V. That means V will be written as Q over C. So that will be integral Q1 to Q2. We will replace V by Q over C dQ. And 1 over C is a constant. Integral of Q1 to Q2. Now, Q dQ can be now written as, I'm going to disregard the limits. We will do the integral without the limits. So that will be 1 over C. What is integral of Q dQ? Integral of Q dQ will be Q squared over 2. So the work done will be 1 over C times Q squared over 2, which I can write as 1/2 of Q squared over C. Alright, so this is one expression for work done in charging a capacitor. And remember, work done in charging a capacitor is a measure of the energy of the capacitor. So what is an equation for energy of a charged capacitor? Energy of a charged capacitor is Q squared over 2C. Q squared over 2C. Can you show that this is the same as 1/2 CV squared? Well, that's not difficult, because Q equal to CV. Q squared is C squared V squared divided by 2C, and 1C will cancel, and that is 1/2 CV squared. So the energy of a charged capacitor is Q squared over 2C, that is one form, which is the same as 1/2 CV squared. So in the first one, it contains Q and C. The second one is in terms of C and V. So you must be familiar with these forms. The energy of a charged capacitor is Q squared over 2C, which is the same as 1/2 CV squared. So if a capacitor is charged to a voltage V, then the energy stored in the capacitor is E equal to 1/2 CV squared, which is the same as Q squared over 2C. Okay, let's do a problem. Half the charge is removed from a capacitor without changing its capacitance. What fraction of its stored energy is removed along with the charge? Well, when you remove charges from the capacitor, from the charged capacitor, you are removing energy from it. So half the charge is removed from a capacitor without changing its capacitance. Well, of course, removing the charge will not change the capacitance. What are we supposed to find? Find the fraction of the stored energy that is removed along with the charge. Alright, let's consider a capacitor of capacitance C carrying a charge Q. What is the energy E1 of that capacitor? E1 equal to Q squared over 2C. And now what is done? Half of this charge is removed. So what is remaining in the capacitor is only half of this. The capacitance C of a capacitor is a constant. That doesn't change. Now, it doesn't depend on the amount of charge on it. You know that. When half the charge is removed, the remaining charge is Q over 2. Therefore, can you write an expression for the energy of the capacitor after half the charge has been removed? If E2 is the energy after removing half the charge, then E2 will be, look at this, energy will be Q squared over 2C. Now this time, only half of the original charge is now remaining. So Q over 2 is the remaining charge in the capacitor. Square that and divide it by 2C. The capacitance doesn't change. And what does that become? That will be Q squared over 8C. I'm sure you can understand that. This will be Q squared over 4, and that 4 will go to the denominator to get that 8C. Now, what was the energy originally before the charge is removed? It was Q squared over 2C. After half the charge is removed, the energy of the capacitor is Q squared over 8C. So what is the amount of charge that is removed? Well, the amount of charge that is removed is Q over 2. Well, let me write it like this. It will be 1/4 of Q squared over 2C. Q squared over 8C is 1/4 of Q squared over 2C. Why did I write like that? Because Q squared over 2C is the original energy before the charge is removed, which is E1. And so, E2 equal to 1/4 of E1. That means when half the amount of charge is removed from the capacitor, the energy of the capacitor now is only 1/4 of the original energy. Therefore, the energy removed, how much energy then got removed, is initial energy minus the final energy, E1 minus E2. What is that? E1 minus E2. E2 is 1/4 of E1. That is 3/4 of E1 is actually removed. What fraction of its stored energy is removed? 3/4 of the original energy has been removed by taking away half the charge. I hope you understand the problem. Okay, another problem. A parallel plate capacitor with a plate area of 2 meters squared and a separation of 1 millimeter is charged to 100 volts. What is the electric field between the plates? What is the charge on the capacitor plates? Find the energy stored in the capacitor. Okay, let's see what are the given things. You know the area of the plates is 2 meters squared. The plate separation is 10 to the negative 3 meter. And the potential difference between the capacitor plates is 100 volts. What is the electric field between the plates? Can you tell me what equation we will use for electric field? We have 2 parallel plates, and you should know by now you have 2 parallel plates separated by a distance d what is the electric field between these two plates? Well, E equal to dV over dr, isn't it? Potential difference divided by the plate separation will give you the electric field. Don't forget that. Those are basic relations, basic equations. So, the electric field between the plates E equal to V over D, potential difference divided by the plate separation. That is 100 volts divided by 10 to the negative 3 meter, and that will be 10 to the 5 volt per meter is the electric field between the capacitor plates. Next one. What is the charge on the capacitor? Well, you know the voltage, and what else do you know? What else do you need to know to find the charge on the capacitor? Well, it will be nice to know the capacitance of the capacitor. Now, is there enough information here for us to find the capacitance of a parallel plate capacitor? What is the equation for the capacitance of a parallel plate capacitor? Capacitance is, all right, kappa epsilon naught A over D. Is that right? Yes, I think so. First, we obtain the capacitance C of the capacitor. C equal to kappa epsilon naught A over D. Well, kappa is 1 because if the dielectric is not mentioned, we will assume that it is air. Epsilon naught we know, A is given, D is given. Use all those values. We get C equal to 1.77 times 10 to the negative 8 farad, which is 17.7 nanofarad. Alright, now you know the capacitance. Once you know the capacitance, we can find the amount of charge on the capacitor. Q equal to CV. Is that right? I hope when I give you these relations, it resonates with you. Now, the only way it can resonate with you is that after listening to my lecture, you go back and do your homework. And also, be active when you listen to the lecture. Alright? Be an active learner. Don't just sit back and listen. That will only make you sleep. Be an active participant. Have a paper and pencil. Always keep writing and keep these calculations current with your calculator. Alright, Q equal to CV. We have now obtained the value of C. We know the potential difference. Therefore, Q equal to C times V. That will be 1.77 times 10 to the negative 6 coulombs, which is 1.77 microcoulomb. Find the energy stored in the capacitor. Well, energy stored is 1/2 CV squared or Q squared over 2C. We can use this. Energy of a charged capacitor is 1/2 CV squared. 1/2 C is 1.77 times 10 to the negative 8. Is it 10 to the negative 8 or 10 to the negative 6? Well, it should be 10 to the negative 6. Yes. You got to make that correction. So you know how important it is to keep up with this and to correct these small printing errors. So that must be 10 to the negative 6. And see if this is correct by making that correction. Alright? 8.85 times 10 to the negative 5 joules is the energy. If it is not correct, you got to do the correction on your own. Alright? Let's go and look at another problem. A parallel plate air gap capacitor has a capacitance of 0.14 microfarad. The plates are 0.5 millimeters apart. A. What is the area of each plate? B. What is the potential difference if the capacitor is charged to 3.2 microcoulomb? What is the stored energy? How much charge can the capacitor carry before dielectric breakdown of the air between the plates occurs? Now remember, a capacitor is useless once dielectric breakdown occurs. So you can't allow that to happen. Okay, let's see what are the given things. You are given the capacitance, that is 0.14 microfarad. The plate separation is 0.5 millimeter, which is 5 times 10 to the negative 4 meter. The charge on the capacitor plates, we need in B part, we want to find the potential difference when the amount of charge is 3.2 microcoulomb. Okay, and it's the air gap capacitor, kappa equal to 1. In part A, what do we need? What is the area of each plate? Well, you know the capacitance, you know the plate separation, you know kappa, you know epsilon naught. We can find the area because the area of the capacitance of a parallel plate capacitor is kappa epsilon naught A over D. The only unknown there is your area. So solve for area from there. Area equal to CD divided by kappa epsilon naught. And you know the capacitance. Is that right? That will be 0.14 microfarad is 1.4 times 10 to the negative 7 farad. D is the plate separation, is this. Kappa is 1 and epsilon naught is the usual value. And that gives you the area is 7.91 meters squared. You notice that the area of the parallel plate capacitors have to be fairly large to construct capacitors of significant value. B, what do we need to find? We need to find the potential difference if the capacitor is charged to discharge. Well, that's very simple because you have the basic definition of capacitance, C equal to Q over V. You have the value of C, the capacitance, well, and we just obtain, and we have the value of amount of charge, do we? Yes, we know the amount of charge, so we know C, we know Q, therefore we can find V, the potential difference. V equal to Q over C, and use the Q is 3.2 microcoulomb, 3.2 times 10 to the negative 6 coulomb, and C, the capacitance is 1.4 times 10 to the negative 7 farad, and that will be 22.9 volt. What is the stored energy in the capacitor? You know the value of C, you know the value of V. The stored energy is 1/2 CV squared. And use the values of C and V. We get the stored energy is 3.67 times 10 to the negative 5 joules is the stored energy. And finally, what is it that we want to find? How much charge can the capacitor carry before dielectric breakdown between the plates occurs? Now, when will dielectric breakdown occur? Dielectric breakdown will occur if the electric field between the capacitor plates is greater than 3 times 10 to the 6 joules per coulomb. The electric field between the capacitor plates, the maximum electric field to prevent this phenomenon is 3 times 10 to the 6. Let's find the electric field first. You know that the electric field between the capacitor plates is sigma over epsilon naught. Now you cannot tell me that you don't know that. That is something that we have been using several times. You have two parallel plates, one charged positively, other charged negatively. The electric field at a point in between the two plates, anywhere, will be a constant given by sigma over epsilon naught. And we can therefore find the sigma. Sigma equal to E times epsilon naught. Well, what is the value of E for dielectric breakdown? E should be 3 times 10 to the 6 volts per meter. So we can now find sigma equal to E times, E is this, and of course epsilon naught is our friend now, so you know its value. There you are, sigma equal to E times epsilon naught, that is 2.655 times 10 to the negative 5 coulombs per meter squared is the charge density, the surface charge density. Well, if you know the surface charge density, how would you find the total charge on the capacitor plates? I think that's simple, because surface charge density multiplied by the area of the plates will give you the total charge on the capacitor plates. Q equal to A times sigma, that will be, area is 7.91 meters squared. Sigma we just calculated, therefore Q, the capacitor plate, the maximum amount of charge the capacitor plates can hold before dielectric breakdown occurs is 2.1 times 10 to the negative 4 coulombs. Alright? Now you can see all these are basic problems we are doing. We are not doing any complex problems. But I want you to be familiar with this. Okay. Let's do another one. A parallel plate capacitor is made by placing polyethylene of kappa equal to 2.3 between two sheets of aluminum foil. Just the same capacitor I just showed you. The area of each sheet is 400 centimeters squared and the thickness of the polyethylene is 0.3 millimeter. Find the capacitance. Well, that's a very straightforward problem, isn't it? Yes? Capacitance is kappa epsilon naught A over D. Don't we have all those values here? Yes. Kappa is 2.3. D, the plate separation, is 3 times 10 to the negative 4 meter. Always remember to use the correct unit. The plate area is 400 centimeters squared, which is 0.04 meters squared. And I think we have everything that we need. Capacitance is kappa epsilon naught A over D. And use all the known values. And just don't leave it for me to calculate. I want you to do that on your own. And that will be 2.71 times 10 to the negative 9 farad. Alright? And that will be 2.71 nanofarad. Alright. I think that will be some representative problems on capacitance. I hope you have a fair idea of what a capacitor is, what it can do in an electrical circuit, and how to solve basic problems using capacitance. Alright, I will get back to you with the second lesson on capacitance. We will look and see how capacitors are going to be used in electrical circuits later on. Okay?